Hello guys, in today's video we are going to learn about an essential divide and conquer algorithm called Fast Fourier Transform, also known as FFT. This revolutionary algorithm paved our way for more efficient data transfer and encoding and used in many applications from different fields of mathematics and computer science. Today we are going to use it to multiply polynomials faster than O(n) to the power of 2. But before getting into the action, let's match our expectations. I'm studying this topic by myself, and my videos depend on the wisdom of the crowd, a topic that really fascinates me. Therefore, if you find any mistake in what I say, please let me know in the comment section below. I promise to read all comments and re-upload if necessary. Also, please subscribe to my channel. I upload many videos on this topic. Okay. So, for starters, let's talk about polynomials. We can represent a polynomial in two ways. The first, using an array of coefficients. The second method is using n+1 points, when n is the degree of the polynomial. Although I will explain in detail in the presentation, the second method, to establish an intuition, remember that you need 2 points of x and y to form a line. And we represent a line with a polynomial of the rank of 1. Y equals x multiplied by const plus const. The addition operation between polynomial takes O(n) time because for each of the nx values of polynomial, we are adding the matched x value of the other polynomial, so a total of n operations. For the multiplication operation, however, for every value, we need to work with all other n values of the other polynomial. This operation requires O(n) to the power of 2 time. We would now see how the FFT algorithm helps us reduce this time to O(n) multiplied by log n time. Alrighty. n+1 points polynomial representation. Given n+1 points of x and y, we can represent a polynomial of the degree n. Converting the representation format from n+1 points to an array of coefficients is called interpolation and requires O(n) to the power of 2. Here is how we perform it. First, we count the number of given points and construct a general polynomial of the respective degree. Say we received 3 points, -2, 1, 1, 4, and 2, 1. We will construct a polynomial of the rank of 2, because 3 minus 1 is of course 2, which means we are getting the general polynomial a multiplied by x to the power of 2 plus b multiplied by x plus c equals y. We will build a matrix by placing each of the given points in its turn in the polynomial. So our points, as you might remember, -2, 1, 1, 4, and 2, 1. And the polynomial is ax to the power of 2 plus bx plus c equals y. Alrighty. So what we are doing here is we are using the x value on the general polynomial, and in that way we can construct our 3 polynomials. Alrighty. Which means -2, 1 is being converted to 4a minus 2b plus 1c equals 1. And 1, 4 equals 1a plus 1b plus 1c equals 4. And 2, 1 is being converted to 4a plus 2b plus 1c equals 1. Perfect. Alrighty. Now, the first step is we would build a matrix with this data and perform Gauss elimination on it. So, as you can see, here is our values and here is our matrix. Lovely. And after we perform the Gauss elimination on it, we are getting the following matrix. Here it is. Great. So we now received a ranked matrix, and for instance A equals -1, B equals 0, and C equals 5. And the set of points -2, 1, 1, 4, 2, 1 are interpolated to the polynomial -x⁻² plus 5 equals 0. Alrighty. Now, after we saw what interpolation is, we would now see the FFT algorithm and how the divide and conquer programming paradigm helps us. As you remember, multiplying two polynomials requires O(n⁻²) iterations. For example, x plus 1 multiplied by x plus 2. So we have here two polynomials of the bounded degree 1 equals to x multiplied by x plus x multiplied by 2 plus 1 multiplied by x plus 1 multiplied by 2. Goal: multiplying two polynomials in O(n log n) time. To do so, we would change the way we represent the polynomials. We would represent the polynomials by points to values. In other words, we would create n couples that include the coefficients and the evaluations of the polynomial when x equals to that coefficient. For example, fx equals 5 multiply x⁻² minus 1 can be represented by its coefficients 5, 0 and -1. The 0 comes because I'm reading this polynomial as 5x⁻² plus 0 multiplied by x minus 1. We would represent it the following way. So f5 equals 5 multiplied by 5⁻² minus 1 equals 124. And therefore, our point to value data is 5, 124. And same for 0. 5 multiplied by 0⁻² minus 1 equals -1. So we're getting 0 minus 1. And finally, for -1, we're getting 5 multiplied by -1⁻² minus 1 equals 4. So our point of value is -1, 4. Our profit from this representation is that instead of having to multiply each variable by all other n variables of the other polynomial, we could add up the values of all variables of the other polynomial and the multiplication would take O(n). The problem is that this process would take us O(n⁻²) because we need to make n evaluations and each evaluation requires O(n) calculations. So for starters, we need to use the first Fourier Transform algorithm to efficiently evaluate the polynomial on these n distinct points. Alrighty, to do so, we would halve the polynomial's length on each iteration in the following way. Given a polynomial, its coefficient representation a equals a0, a1, a2 all the way to an-1, we would divide the polynomial into two polynomials. One includes its odd coefficients and the other its even coefficients. Assume n is even, otherwise adding another 0 coefficient in front. So a even equals a0, a2, a4 all the way to an-2, and a odd equals a1, a3, a5 all the way to an-1. Notice that a even of x⁻² plus x multiplied by a odd x⁻² equals ax because of the following proof. Alrighty. The problem with splitting the algorithm to two is that the bounded degree of the polynomial we're working with is not the same, and also the number of distinct x values is not the same. Therefore, we need to introduce two properties. The weak negation property. A list of x points, x0, x1, all the way to xk minus 1, is said to have the weak negation property if either k equals 1 or if for every integer of j between 0 to k divided by 2 minus 1 we have the following. So for example, the list minus 1, 2, 1, minus 2, or minus 3, 1, 7, 3, minus 1, 7 as the weak negation property, while minus 1, 2, minus 2, 1 does not. That's because, as you can see, the first value of the set does not match the third value, and same with the second value. Unlike on these examples when minus 1 indeed match 1 and 2 indeed match minus 2. The problem with this property is that it doesn't guarantee that after a recursion, a weak negation property list would keep its property. For example, the list minus 3, 1, 7, 3, minus 1 and minus 7 is split to minus 3, 7, minus 1 and 1, 3, minus 7. Remember, we divided the even indexes from the odd indexes, which no longer have this property. We would introduce a stronger property. The strong negation property. A list of x points, x0, x1, all the way to xk minus 1, is said to have the strong negation property if either k equals 1 or if the list has the weak negation property and x0 to the power of 2, x1 to the power of 2, x2 to the power of 2, all the way to xk divided by 2 minus 1 to the power of 2 has the strong negation recursively. A list of numbers fulfilling the second condition of the strong negation property is the nth roots of unity. A complex number is written in the form of z equals a plus I multiplied by b, where a and b are real numbers. An alternative way of representing a complex number is z equals r cosinus theta plus I multiplied by sinus theta equals r multiplied by cis theta equals r multiplied by e to the power of I multiplied by theta. Geometrically, the roots of unity are spread evenly around the unit circle, and means we are taking complex roots of 1. Also, it is clear that only a list on the length of some sort of power of 2 can satisfy the strong negation property. Hence, if the given list is not the power of 2, we would add a bunch of zeros to make it 1. For example, we would convert the polynomial x to the power of 2 plus x plus 1 to 0, x to the power of 3 plus x to the power of 2 plus x plus 1, and in that way we received 4 numbers in our coefficient set, the halving lemma. Let n larger than 1 be a power of 2. Then the squares of the omegas, which are the nth roots of unity, are the n divided by 2 complex n divided by 2 roots of unity. We would now look at the FFT algorithm to evaluate our polynomial in O(n) multiplied by log n. Alrighty, so this is our algorithm, and this is our base condition. If n equals 1, we are simply returning a 0. And here we actually divide the polynomial into its even coefficients and odd coefficients, and here we are returning the process recursively, and finally we are returning this vector. Alrighty. Explanation. We want to compute the values of A at the x values that are the n complex nth roots of unity of order n. The returned values define the returned vector y equals y0, y1 all the way to yn minus 1. If n equals 1, then we return ax equals a0, as I said. When x equals 1, 1 is the only root of unity when n equals 1. So we return y0 equals a of 1 equals a0. In case n is larger than 1, we will implement divide and conquer principles to half divide the given polynomial to smaller subpolynomials in a series of recursive calls. In line 4 of the algorithm, for example, the algorithm computes the values of a even at the x points that are the n divided by 2 complex n tag divided by 2 nth roots of unity, which are the following. The recursive calls returns an array whose values are p even equals a even of this nth root of unity all the way to this. A similar occurrence happens at line 5 with p odd. So yj equals a omega jn equals a even omega jn to the power of 2 plus omega jn multiplied by a odd of omega jn to the power of 2 eventually equals to p even j minus omega jn multiplied by p odd j. Multiplying. We would call the coefficients x0, x1 all the way to xn minus 1 and call that list the x tag vector. There is special matrix called Vandermonde of the size of m rows and n columns. The unique aspect of this matrix is that its columns are built with unique numbers and each column represents the same numbers just with a higher power. For example, for the values 1, 2 and 3, this would be its respective Vandermonde. The first column all equals 1, the second column equals the numbers themselves, and from then we are using the numbers on a higher power. So the third line is to the power of 2 all the way to the nth column, which is to the power of n minus 1. I would not get into much details regarding this matrix, but I would say that it is invertible. I mean, by multiplying it by v minus 1, we would get the identity matrix. Also, by multiplying the Vandermonde matrix by our vector x tag, we would get Vandermonde multiplied by x tag equals ax0, ax1 all the way to axn minus 1, which equals to y tag, which equals to y0, y1 all the way to yn minus 1, which are exactly the values our algorithm returned. We will multiply both sides of the equation by the invertible matrix of the Vandermonde and get x tag equals vn minus 1 multiplied by y tag. And since we already computed the value So the same algorithm also works for multiplying, which is great. And that's it. Basically, we showed where we can multiply polynomials using first Fourier transform in O and multiply by log n time, which is great.
Well, that's about it. I hope you learned something new from this video, and please comment below with your thoughts. First degree studies in university are all about social studies, and this project comes to encourage that, even through complicated situations most of us are going through right now. Please subscribe to my channel. Until next time, good luck!